It's really a great pleasure to introduce our today last speaker, and that's Kai Strehlke. Kai Strehlke has just a bit more experience than our previous speaker, and
older.
Yeah, something like that. And he was researcher and he lectured at the ETH Zurich. And from 2005 to 2015, he established and led Digital Technologies Department at the Office Herzog de Meuron, and he was responsible for lots of the projects. Then, 2015, he was a guest professor at our institute, at the Institute of Architecture and Media at the Graz University of Technology. And since 2015, he's leading again, and he's head of the department at the Blumer and Lehmann for all of that CNC manufacturing on a really large-scale timber structure. And I'm curious to hear your talk today and about your project, and see you later.
Thank you very much for the kind words. I'm very honored to be here, and I totally feel at home, standing in this dome completely done in timber. That's a little bit like being at work. So I will present you a little bit of the company and then 5 projects we were doing in freeform timber. And I will explain the differences between these 5 projects. I feel a little bit awkward because when I saw this brilliant geometry von Eike, I think that we do just the opposite. You know, we do a lot of energy to get these free forms, but that's all I can present. So this is where I'm working normally. This is in Gossau. What I'm totally amazed of, the company is 150 years old. It started as a sawmill. And there's a very small creek. And in this creek, there's no water. And to me, it's a big thing to imagine that someone came to this idea to make a sawmill with this very little energy, and how this big industrial village came out of it in 150 years. So this is when I started, and now we just pushed the creek on the other side, and I think the company doubled the size of production facilities in the last 5 years. So it's still a family company, and Katharina Lehmann, she's the CEO of the company, and she's really the person workshopping all the 150 years of timber work, but she's also the person who's really looking in the next 150 years what is possible to be done in timber. And she's very much interested in working with research institutes and work on projects, maybe once with Eike. So we are very interested in closing the value chain of wood. We have the sawmill. We are cutting the wood in our sawmill, and then we are producing architecture with it. And when we cannot produce architecture, we take all the rest to make pallets, or in the end, we burn it and we create the heat and the electricity for our own company. So basically, in 2 images, we start here and we finish there. That could be my talk, and that's done. So the portfolio of the company, just to show you a little bit what we're doing housing. I studied architecture in the last century. When I was studying architecture, this was impossible. You could do like 1-story buildings, 2-story buildings in wood, and then fire regulations did not allow you to go higher. So what we're experiencing at the moment is incredible. What is possible to do in wood now, I feel a little bit like in the modern times when Mies van der Rohe was designing architecture in steel and glass. I have this impression we are living now in this moment where we can do similar things in wood. So hotel industry, I just flip through it. It's a gastronomy. It's a very beautiful building from Herzog de Meuron in the mountains of Switzerland. More and more industry and commerce is done in wood and timber rather in steel. That's an interesting building from Shigeru Ban we have done in the center of Zurich. Wood has been kicked out of the cities in the 17th and 18th century because big cities completely burned out. So our cities became stone cities and later on steel and glass. And what we're experiencing now is that the timber is coming back into the city and it becomes again an urban material. Then extensions, something which is very important, because when you want to make a resilient architecture, it's important not to tear down everything, but to just take what you have and build on top of it. Modular architecture and freeform architecture. The freeform architecture started at Blumer Lehmann 13 years ago, and that was long before my time. And the step from Katharina Lehmann is quite incredible. She signed the contract to do this building for Shigeru Ban in Korea. And she was sitting with 13 people in one room, and they said, do we do it or do we don't do it? If we do it, we don't fight against each other, we work together. They signed the contract, and afterwards, they bought the CNC machine. They got the people who were able to work on it. They constructed everything, transported everything to Korea, and assembled everything. And from signing the contract to doing all this were 6 months. And now we've done 6 other buildings for the same client in the last 2-3 years. This is a building where you see the trees on the top. This is a kind of pond. And then we have a building below. This is like the room below, and you can look through the water into the air. And you have then trees on the roof. And so when I was studying architecture, a lot of projects or a lot of companies became bankrupt. I think from the Wolke in Graz, a lot of companies really lost whatever they've built up. And Blumer Lehmann is still alive. And I think what makes us so special that we are able to do these buildings and other people are getting bankrupt. And I think what we do is, because here you see 4 different kind of tree structures, and they look alike, but they're super different. And some of them, like this one is the Grand Tolling Yochu I just showed you. And the Cambridge Mosque is like, if you compare these 2 things, this is a football league of a regional classic Liga, and that's Champions League. And it's very important to really understand the geometry. It's very important to really understand the building if you want to go into a contract. And what we're doing a pilot. And the pilot we do before the submission. This is in public buildings, you're not allowed to do a pilot. As a constructor, you are not allowed to get in contact with the architect before the submission of the building. And this for us is super important. When we work with Norman Foster, very often he comes like 2-3 years before the completion of the building to us to really develop the building together with us. So it's a feasibility study, 3D model. We get quite a good cost estimate after doing a pilot or mock-up. And we already work with a 3D model. So it's already a kind of, between the architecture, the structural analysis, and the production team, it's quite important. For example, architecture, structural analysis, architects want to have very slim architecture. Structural analysts want the architecture to be resilient enough to not to break down. And between structural analysis and production, tolerances are very important. The structural analysis does not want to have so many tolerances, and we want to be able to assemble the building. So these are quite important to solve on mock-ups. Here it's a mock-up of a building I'm showing you later on. And if you look closer into the beams, you see that some layers are laid in one direction, others are laid 90 degrees. And when you look at the wood, which we are using, the timber, the cubic meter of wood differs from 1 to 15 in price. So there are like things, if we do all the buildings with this kind of wood, it would be 1 million. If we do it all the other way, it's 15 million. And this is quite important to really grasp these figures very early in the project. And another thing which helped, which we noticed, is whenever we do a mock-up, it becomes real, like it's the first manifestation of the real architecture. And this is really nice, and it helps decision makers to go forward. Like I worked for Herzog and de Meuron on the Elbphilharmonic building in Hamburg, and there were like years of stagnation of the construction, complete stagnation, and years of, and you really noticed that the key figures were difficult. It was difficult for them to take decisions and know exactly how we are moving forward. And the mock-up is helping there a lot. So now I'm showing you 5 buildings. The first one is very handicraft, like we're not using any robots for it. It's a pavilion we've done in Ohio, in the USA, on the outside, and we worked with Accoya. So also already here we used these very small Accoya sticks, glued them together, and then we created a jig and put a stick inside. Glued it, took it out, and then we left it on the roof of our building over one winter just to see how the wood is really reacting, how the Accoya is reacting, if the glue is really staying inside, and if we are daring to do a project with this. So after doing it, we had a 3D model, and this is just the opposite of what Eike has done. Like now we are using a huge amount of material to create the jig, and on the jig we are gluing all these sticks together. We take them out, we sand them, and then we ship them all to the US. We use the same jig and build everything together on site. So that was, I think 8 years ago when I came to the office, that was the first project we have done. I was like connected to the project. And the second project is a mosque from Marx Barfield. It's in Cambridge, in England. And Marx Barfield wanted to make a mosque which is not a mimicry of the blue mosque of Istanbul or any kind of Arabic mosque. He wanted to create a sacred architecture which fits into the English Christian world. So one concept of doing the mosque was, like he said, he wants to create a garden for the praying, plant trees, let these trees grow, and then have a roof of these trees. So that was like one architectural inspiration from him. The second one, he worked with Professor Keith Critchloff together, who is also a professor of architecture, and he's a professor about Islamic patterns. And they tried to find a way where they combined the idea of the sacred Christian architecture. There's Kensington Chapel, make a relation to this kind of architecture, and at the same time work on Islamic patterns. And this pattern here is a geometric pattern, and when you look on the second image, you see a form with a positive negative. And this symbolizes on one side like the rhythm of life, like breathing in, breathing out. And it's a symbol of Allah because you can continue this pattern forever. And out of these patterns, they created a kind of geometry, and they wanted to transport this geometry into the architecture. So no geodesic curves, no like geometric optimized thing. It's a pure pattern which is then translated into the geometry. So this is how they came to us, or to design to production. And the first thing, design to production, is always working with a reference geometry and then working with the of lines on which this reference geometry is going on. And if I would have done this at Herzog and de Meuron, I would also have taken a mass surface like these rotational things and then a flat surface more or less on top. And they used a different master surface, which also was later translated in where the joints were. Because very often when you have a joint in a surface, you have bending moments at these positions. And then a second important thing is at that time, all the BIM software was still mesh organized. So when we work with 3D geometry, we absolutely need NURB surfaces, because when we have a mill, when we are milling a surface, we really have to mathematically follow a NURB surface to have a very smooth surface in the end. And even if you work with a mesh surface, you always have a small triangle. So you have the drilling bit which goes in a triangle, it turns to the next one, it makes the next triangle. And it looks like stupid, but you see these things and you hear it on the machine if you have a very smooth movement on the machine in the end, or if you have like a mesh movement. So the first step in this project was to work with the master surface I talked of and the geometric pattern. We projected this into the surface, and the engineer defined the thickness of the beams. What we don't know at this moment is the segmentation of the beam. Like, we could do this with very long beams, or we could do it with thousands of small beams with a lot of connections. You want to do it with as long beams as possible to have a very stiff structure. And, but this is like the problem of how do you join these things and how do you look at these things. And what we are doing here, we do an analysis of the curvature of these beams. Because we can work with 3 types of wood. We can work with straight blanks, singly curved blanks, and doubly curved blanks. And we have to use the fiber of the wood, of the timber, in the direction of the construction for the strength of the wood. So when we want to work with like bent wood glulam, there's a rule: the radius divided by 200 gives you the thickness of the lamella. So if you have a radius of 8 meters divided by 200, you get a thickness of 40 millimeters. 40 millimeters is an industrial lamella. Eike told you we're talking about the thin lamellas. So for example, the thinner it becomes, the more expensive it is. And here you can see this is like just a chart which is giving you an overview. Straight wood, you can work with 40 millimeters lamellas. This is not a problem. Singly curved wood, you have to make the lamella maybe thinner if the curvature is smaller. And in doubly curved wood, the price of the cubic meter can go up to 15 times. Depends on the thickness of the lamella. And why don't we take just big, cheap wood and cut everything out? Is because we have to follow the fiber angle of the wood. If you would take a piece of wood and you try to pull it along the fiber, you will not be able to break it. If you turn it 90 degrees, you're able to, if you make a karate cut, you would be able in one direction to do it, in the other one not. And for buildings, for the swatch building we have done, we get from the engineer a fiber cutting angle in which the fiber has to follow the structure. And this is normally by 5 degrees. Within 5 degrees, we are allowed to cut the fiber, and then we are losing all the compression and tension strengths. So how we are doing this wood? Like straight wood is very clear. Singly curved wood, we have already catwork machines which are putting all the jigs in place. We can place these lamellas inside, lamellas up to 28 millimeters, normally 40 millimeters thick. If we want to do doubly curved wood, we take these singly curved wood and then we slice it like a salami. And on a second step, we take these salami things, we build a jig, and then we are putting these things in the jig. This explains a little bit the difference of price between straight wood and doubly curved wood. And then you don't have lamellas anymore, but you always have a cross-section in it. So one difficulty of doubly curved wood, it's expensive. So what is the guy who is doing the buying of the wood? He's like optimizing. He's putting us like, instead of 2 centimeters of extra wood on each side, he puts us 1.5 centimeters. The second problem is the wood is under tension. If I would click and take the glue out, everything would become straight again. So there are like spring-back forces happening on the wood. So even if the wood is glued like this, the reality is a different one. And then the big issue is how do you put it on the machine? Because if you have no straight, flat surface to put it on the machine, and this is quite a challenge to create these objects and put the doubly curved wood on the machine. So now we have segmented it, and we have put the joints inside, and in the end, we are building a Lego system for the whole structure. So this is how this Lego system looks. We are talking of trees. We have 145 different types, 2,746 individual pieces, and we cut them out of 23 types of raw blanks, doubly curved, singly curved, straight blanks. And we work, like in this project, we work together with Design to Production, and they gave us this kind of system where, for example, you can see all the different kind of blanks, like X3 is one type of blank, and then you see what kind of types have to be cut out of this blank, and some of these types have to be cut out 145 times, and other ones only 2 or 3 times. This is then the big problem to do. And then afterwards, we are going from geometrical CAD data into reality. So in timber industry, you can work with straight wood, and you have Honecker machines, which are super industrialized. You can work with plates, where also Honecker has very industrial solutions. And when you work like in this freeform timber, you use a lot of CAM software, which is also existing in the car industry, like normal CAM software. And it doesn't make a big problem if for Mercedes-Benz you make a form and you use 100 hours to do the CAM thing because you know that this piece is going to be used 10,000 times. But in some buildings, like in the Swatch building, we had 5,500 pieces, each of them with a different geometry. None of them, there was no repetition inside. So there we worked on Rhino and Python. We are creating our own scripts. We are creating our own simulation to look if the things are working. And this is how it gets on the machine. It's like a Swiss machine from Technowood. It's a standing portal, and then we have carriers where we are putting the wood into the machine. And in our case, there's always a guy controlling every movement of the machine. Like only if we do repetitive things, they go and have a coffee, but normally they're always there. And the problem you see, it's when we are milling there and the machine would turn, then we are getting a collision because the height of the spindle. So this is like one problem. This is another one. When you look at this, you think that this person is looking at this part, but the collision happened here on the bottom. And can you see it? No. So the collision happened on the bottom. And therefore, we are simulating everything. And we try in prefabrication to make all the complexity in the factory, put all the steel stuff inside the factory, clean the wood if they're like glue coming out, or hardscallen, resin coming out. There are different ways of using steel rods inside, which we are gluing inside, or just with plates. But this is all done in the factory so that in the end, on the construction side, it becomes a pure Lego system, if everything is precise. And for a building like the Cambridge Mosque, we had 60 to 80 trucks moving from Switzerland to England. Not very sustainable. You could think they could use their own wood and do it there, but we are producing it all over the world. We are working in Korea, we have just done something for Foster's in Saudi Arabia where we shipped 800 containers. And then when we work in England, like everything is put in foil, also not very sustainable. Like freeform is not sustainable. Let's leave it there. When we put it on site, we have to wait for a sunny day because we cannot work. Wood is very reactive to humidity, And when we are cutting the wood, we are drying it in kilns, we are gluing it together, and from that moment we keep it always at the same humidity until it gets on site, until it gets into the assembly. After, we don't care anymore. Then the building can do a little bit what it wants, and normally the building starts to dry out to like from 12% to 6%, but then it's assembled. Then things happen. Then wood is cracking. If you look here in the timber construction, you will see thousands of cracks, and you still dare to stay here. So when there's a good weather, we start to work at 3 in the morning until 3 in the morning, like we do whatever we can to assemble the building. Here, they're the trunks of the trees. Here we call them the crowns of the trees. We have a roof where we pre-assemble what we cannot assemble in. It doesn't make sense to transport a crown like this from Switzerland. So we pre-assemble it, and then we put it into the building. And there's a very big difference between the architecture from Frei Otto, because when you look at this and you say, wow, this can only be done with digital tools, Frei Otto did the same without digital tools, but with a different philosophy. Like, he put everything straight on the ground. He worked with these tolerances. He put the whole form in place and then fixed everything. Here we are working with a super stiff part. And this part, from one side to the other one, allows a difference of 1 to 2 millimeters. So it's freeform like Frei Otto, but the philosophy, the logic of building it is a complete different one. These are just a few construction sites. If everything fits together, people are happy. We work, the yellow ones are from Blumer, Lehmann, the red ones are British people, because when we work, we always have our own people on site, but very often we are not allowed to use a crane, we are not allowed to use a akubora, we are not allowed to use anything in some countries. So you always have to work in combination with local carpenters. And this is an image of the final building. And now comes another project. Now they're very short. This one was a little bit longer. This is a complete different way of bending the wood. You see, when we bend the wood, we stress the wood in shape. Here we work with Achim Menges and the University of Stuttgart, and here we ask the wood to bend itself. You, of course, all know it, but very often when you have people from the timber industry, they have no clue how it works. So we're working with a belayer wood. So we have one level, a thin level, which is in one direction, which is super dry, and the other one, which is super wet. We glue it together. When the humidity gets the same, then you get a kind of curvature of the wood. And we're using this kind of banding. That was a project together with the Emperor. They calculated everything, and out of this logic, you can see here these pre-bent panels. We put them in a big jig, and then we are just gluing these panels together and milled whatever we had to mill and pre-assembled as much as possible in the factory. And then we could go on site with one truck and assemble the whole thing in 2-3 hours. That's third way of bending wood and working with three-form structure. And now number 4. Number 4 is a project we have done in Delhi. The design is by Ursula Frick, who worked also at DTH. It's done out of 101 individual pieces, but the specific thing is that the radius is very small. It's 800. 800 means 8 millimeter. And we worked a lot of how we could connect it, that you can't see anything. And the problem when we work with these 800 and we have only 8 millimeters is that we have the springback forces. And the wood should have been done in ash. Or they wanted ash. So if ash is a super wild wood, it has a very wild kind of, Maserung. And when you have a thin layer, and you're cutting from one to another one, you can imagine that one layer is very dark and the other one is very light. and you cannot control it because of the spring-back forces. So you have a kind of very strange pattern which might appear, which is very ugly. So we wanted to have a very thick layer, which we cannot, because if we would bend it normally, it would break. And what we have done, we used the same thing, how do you do a tonne stool? So we put it in this oven, heated it, and then we could bend like 60 milliliters of wood in one row. And these ones were afterwards glued together. Normally, when you're bending wood, you're stretching the fiber. Here, we are compressing the fiber. We don't get any certification for construction. It's okay when you work in India. It's okay when you work in Switzerland. If you work in Germany, you could not do this, and Austria also. And then we assembled everything. It worked quite well, and you see absolutely no steel, nothing, no connection in the end. And now the last project is a project we just finished in Sweden, in Stockholm. It's the Visdom, and here we are working with active bending. So we had in our scope the dome inside, which is not so complex, and the roof. And the roof, we wanted to do it with, like it was done together with Stora Enso. They do LVL. And the idea was to have like super straight wood and only bend it inside. And again, for every project we do mock-ups. So we started with Blumer, Hermann Blumer, who's the Pope of wood in Switzerland. And we started to imagine, because we had wood which was bent, we had torsion inside, and we tried to understand how does it really work in, with the material. And we started with a small test, and afterwards we decided we make a big mock-up of one of these crosses in the scale 1:1. And Hermann Blumer said, it's very easy, we do these mock-ups, we do these dowels, we are putting it in shape, we are cutting the dowels, and then we are hammering in the dowels, and the wood will stay as it is. And this will work. So even if he said it, we did it. Like we made a jig, we put these LVL levels in place, and afterwards we milled, we put the dowels inside on the right side. On the left side, you see what happens if we took the screws out. So everything was going back, spring-back forces, like a complete failure. And it was quite interesting. I was standing there. I'm an architect. I'm not a timber carpenter. So I was standing between Hermann Blumer and a carpenter. Both of them, like he is 80 years old. He's the Pope of wood. And on the other side, someone who had like 30 years of experience and who really knew wood from everything. And the guy on my right side said, no way, we have to get out of this project. We are burning our feet with this project. And Hermann Blumer looking on the other side, but it works a little bit, no? And I was like, wow, two experts saying two completely different things. And we screwed everything together. It's far away from the geometry which it should have been. And we said, okay, we need a second mock-up, a longer one with a torsion. So second mock-up, exactly the same thing. We milled everything, we hammered the whole things inside, spring-back forces of 16 meters, 1 meter 20. And normally we are afraid of like spring-back forces of 2 centimeters and then 1 meter 20. And then they said, okay, we do it. We do it rather than having like 4 levels, we do a 5th level. We are not using 5 lamellas of LVL, 4 of them, we use 5 of them, they are thinner, and then it's going to work, and we work on these knots. So the geometry of these dowels became much more complex. Here you can see it. The project, I think, was sold before this mock-up, which is not so good. And then Stora Enso was supporting. They were like doing it was for them a project to manifestate what they can do. And they came and they said, because we had to segment everything, they said, you have to segment it now. And we said, we have no final geometry. We have no final connection. And they said, yeah, but we have our companies in Finland and Sweden, and we need it now for production. So design to production was doing all the segmentation of the wood, so they could like pre-order the LVL with no connections inside. And they did all the transportation, everything was like decided, and only 2 months later, the whole construction, detailing, everything was added into the geometry and then like calculated back into whatever has been nested before. And then we did a last mock-up. A complex mock-up with torsion and everything. And here you can see a fast speeding way. And what we've done is like the first layer, we glued it in the company. So we said we have to glue the first layer and all the other ones, we are putting them with active bending inside. Otherwise, it does not work. And this now is the final image. It shows you a little bit the atmosphere we have in our company, like super silent, beautiful music. So we are doing jigs. And there we are pre-gluing the first layer. And these parts were transported to Stockholm, and all the rest was done with active bending. Thank you very much for your attention.
Thank you, Kai, for speaking also about material and about the problems, because sometimes the architects have only the nice images and we cannot see the problems. And that's really the big, big problem, because we should face all of the problem with material and with geometry, and everything works only together. Do we have some questions from your side? Please.
Hi, thank you. Thank you, really inspiring talk, and thanks for showing the difference between research and actual practice. I'm really fascinated that you're actually bending in several different ways, by steam bending or by or glue laminating, or now real bending, and you always have that spring back issue that you mentioned just now. I was wondering, how much do you go to simulate the spring back, and do you bend it more during construction than to get to the right geometry, or how do you actually tackle it in the very end?
It's like the question with the robots, we are not. The problem is we are not simulating it. The thing is when you cut a piece of wood, you have one lamella. One lamella has a part which is under tension and a part which is under compression. If you put a second lamella on it, you have again tension, compression, tension, compression. So it's not one beam which one tension and compression side, but you have each lamella is doing its own game. And when you start cutting into one beam, the spring-back forces are resulting in like opening it and closing it and opening it and closing it. And this is not predictable. So the strategy we are doing normally is that we try to take as much roughing material away as possible so that the piece we are constructing is, the beam is like stable, and then only we are surfacing the last things, and the most critical parts, we do them in the end. So that we know that, for example, if I have a beam of 16 meters, I'm doing the cuts in the end, I'm doing the slots in the end, and then I know that the slots are correct to each other. And very often also when you look at the beams here, it's the connection which is important. Between the connection, you don't care if the beam is really doing the curve or is doing something different, and you're not able to perceive it because it's a lively material. So we are not simulating it, but we have a strategy how to work with it. And the tower of Remstal, the pre-bent wood, there's no stresses inside. Because you have like wet wood, dry wood, and then it bends, and then it's like, it's quite okay. But the problem, the very big problem, we're doing another tower now, is the gluing. Because all these glues are certified with certain kind of millimeters and thicknesses and whatever. And when you have this and it's not really bent in exactly the shape you want, you really get problems with the glue layer, the thickness of the glue layer.
Thank you very much. The second question.
Thank you for your talk. I know many of these problems. There have many questions, but maybe just one here. We had also the problem, we milled the wood very precisely with Christian, Christian Freisling, and we couldn't work for 1 week. We had to put it somewhere in a house, and it was very warm, and after 1 week, wood was different. So how much time do you have at the construction site to really assemble all the parts? Because this must be a very big issue if you have so many parts and so big projects.
Like very often, freeform projects take quite a long time. And we are the last moment of this production, or assembly is the last position of this process. But production comes just before assembly. So very, very, very often, we don't have digital data, we don't have the wood, but we have the trucks waiting already to get on site. So very often it's a very short period in it's really just in time. For the Swatch building, the beams we were doing 2 days later, they were in the building. So it's normally very fast. But glulam is also very stable, because if you have a pure beam, much more things happening. We've done once oak, it looked like a cigar, a huge oak tree, and we milled it like a cigar. And when you looked afterwards, the whole tree, it's like completely filled with cracks. You really have this impression you can look through the tree, and you have this impression, oof, and it was like holding a huge building. And it works, but if you work with glulam, it's much more stable, homogeneous.